Thanks very much. My pleasure to be here. While you're staring at the picture of the latest ALMA pictures that were just there at the inauguration a few days ago, let me note that this afternoon, all three speakers, namely Jim Moran, Ron Allen, and I, had the same thesis advisor. Some of you may not know that, which is quite amazing, and the reason, of course, is because Ron and Jim are so much older than me.
I'm wiser.
People, you should be one to talk, right? Whether you're wise. But somehow, years have passed, and I've gotten older, and these two guys still look the same. And catching up to them, and what I want to tell you is what Ron had told us when we had a 60th birthday party for Al Barrett, our advisor. At the time, Ron says there was a reason why we all happen to be radio astronomers, and he says it was actually an accident, because when he was a PhD student, the first thing at MIT we had to do was to find our funding source. So he had a list of professors, and he was going down the great hall, down the hallway at MIT, looking for the professors to see who had a job to hire them, right? So when you get down to the end of the corridor, see, Ron, I remember everything you said, and get down to the corridor, he was about to turn right, except the guy wasn't there in the office, so he turned left to building 26 and got to see Al Barrett. He says, I walked into his office, and I didn't ever come out again. And had Al Barrett been an oceanographer, he says, today all of us would have been sitting here talking about oceanography. So the point of the story is, your advisor, people, is extremely important, right? If the advisor is enthusiastic and infectious with that love for research, it doesn't matter what that is, because in science there are so many things to do. You're wondering where I'm going with this story. And the reason is I know Luis very well from when we were graduate students together. Okay? So Luis is cut from the same cloth. He and Yolanda is so enthusiastic about his research that if you walked into his office, you too would not have been able to escape. So congratulations on this Radioastronomy Institute in Mexico, which has grown very well over the last 10 to 20 years. Okay, so.
You know.
The yellow button, yes. So here's the picture. So these are the important people in Taiwan in the development of ALMA. This guy over here, who claims to be so wise, was the guy who got most of us into Taiwan to push for astronomy in Taiwan. The gentleman to his right is named Wu Ma-Guan. He's actually a low-temperature physicist, but he actually worked on a high-temperature superconductor. And he's the guy who actually allow us to convince him that we should join ALMA, because at the time he was the head of the National Science Council, the science funding agency. And working with excellent people with good judgment and with good vision is the key to building good science. Okay, so ALMA, I show you this picture because it's inaugurated, it's starting to go, but as every project starts to go, we should be thinking about the next one, and we have been thinking about the next one. So the next project is to go to Greenland. So here's a picture. You can see it's white. It's very cold. Okay, so for us, our project team has 4 partners. This is Smithsonian and the Institute in Taiwan, the academic Sinica Institute of Astronomy and Astrophysics, and of course Haystack and NRAO. For us old MIT boys, we know these places quite well. We've been working with them, and they have the experiences in principally working in VLBI. So this is an experiment to carry on with VLBI in the submillimeter wavelengths. Here is a picture that you cannot see in the details, okay? The important thing to note, this is a science case building about how we want to build the Greenland telescope. And the science case is mapped into the decadal survey that has been just completed in the United States. And 2 of the projects that were mapped into this decadal survey that we're specifically looking at is the Event Horizon Telescope and CCAP. Both of those telescopes rely on having good sights and working at high frequencies. Okay? So from those two projects, we can map the science requirement, we can map the antenna requirements, etc., to build the case. So here we are, our target, a nice cold place at the top of the universe, as defined by the Earth. North 72.5, okay, pretty close to the top. And here is the site as you can see it. Okay, the site is dominated by these things which are, they're storage places, but people stay in this thing called the big house, which is over here. And here is a picture of a big house in the middle of winter when the sky is dark, because it's north, of course, most of the winter time it is dark outside, and you can see the nice green aurora going, which means that you are pretty close to the pole. In the summertime, if you are out there working, you will have to live in tents because there's no room for you in the big house. So sleeping out in cold temperatures is a requirement for you to work there. So here's the basic description of the project. The scientific goal is to image a supermassive black hole, hopefully for the first time, or maybe the second time, depending on how it goes with Sagittarius star, and to measure the spin of a supermassive black hole also for the first time. Note that for a black hole, there are only two properties that we can think of measuring: the mass because of gravity, but in this case, not because of gravity. We're actually looking at the imaging as a second means to measure its mass, as Jim has shown you earlier, and then also to measure the spin, in the sense that if there's spin in a supermassive black hole, it will influence the metric around it, and therefore the radiation coming past it will have a different pattern, which we can use to measure the spin of the massive black hole. So this project began roughly about 2 years ago, when the telescope, the primary telescope that we're talking about, a 12-meter prototype telescope from the UNAM project, was awarded to a team led by Smithsonian and ourselves. This 12-meter telescope has a value of maybe $8 to $10 million. It is the prototype from which the North American contingent designed their telescope for the whole ALMA array. We compute that the project will cost about $24 million. We are raising about 14 in Taiwan, and Smithsonian is raising about 10 million. I've also put down here about 22 million from NSF, and the reason is that they too are interested in our project, and the main reason is that their work at the pole is on ice core, which means that they're examining the ice properties over the entire history of the Earth by drilling down 3,000 meters worth of ice core. So therefore, they are very interested in keeping the ice very pristine, and they would like to move all the dirty stuff onto our site. That is their interest. And here's the timeline. As I was putting together this talk yesterday, I already had to move the timeline by 1 year. It used to be 2015 for first light. And you know why that is? This is the economic crisis in the world. It's very difficult now to gain funding and to push the project forward, which I'll explain. So from Taiwan, this project is a culmination of our radio effort. So in Taiwan, we have two paths. One is radio, one is the optical instruments that we've been building. But in Taiwan, we've been committed to do the SMA, followed by this cosmology project called Amoeba. Then we can start to do the ALMA, and while doing the ALMA, we're thinking about the Greenland telescope. And here's the timeline, SMA, which Jim was the director of when we finished building it in 2003. And then these products have now been delivered, and now we're aiming at this Greenland telescope. Okay. So again, the objective is to directly prove the existence of the supermassive black hole by being able to see the shadow itself. Measuring the shadow is to measure the metric. And this, if successful, we will test the gravity, strong gravity cases at the surface of or close to event horizon in order to test general relativity properties, and also, as mentioned, measuring the mass and spin of the black hole. So here it is, for example, in the galactic center. This is the best image that we can make at the moment with the VLA. It is a spot, it is a point-like source. It would be difficult to know what that was, except for the stellar motion, the orbital motions that Jim showed you, which measured that the gravitating mass here is extremely high, on the order of several million solar masses. However, if you improve the resolution by a factor of, say, 100,000, you may be able to see the actual accretion process onto a black hole. and the shadow projected against this accretion process. Okay? So the astrophysics related to the supermassive black hole is the target ultimately when we have enough information. So the question is, which is the best target out there to look at? For a long time, of course, we thought the galactic center was the best target because it is the nearest one. However, the measuring property of a black hole is actually mass over size. It's not density. Mass over size. Therefore, the bigger the mass is, the bigger the size, scaling linearly. So if you can find a very large black hole, you will overcome the distance effect. Okay? So here's the galactic center, much closer to us as compared to, say, M87. But M87 is much bigger than supermassive black hole. It's about 2,000 times or so more. So it almost compensates for the distance. In its size, depending on the mass, there's some slight difference of opinion as to how much mass is in this black hole. But it's on the comparable to the size of Sagittarius star. Okay? The next ones will be much smaller. So, in order to image it, then comparable distances in terms of VLBI distances will be required, and then we can see that if we have somewhat longer baseline than what we're projecting for Sagittarius star, we can also do a good job on M87. But now, what is the intrinsic property of M87 that is interesting to us as compared to galactic center black hole? Actually, it's the size. Okay? Because this black hole is bigger, its rotation period is longer. Okay? So for the galactic center, we expect that it will spin on the order of minutes. Okay? But for the supermassive black hole in M87, it's days to months. Okay? That tells you that in the VLBI experiment, if you're imaging, you have to be very careful what's happening because it is rotating as you image. But for M87, there will be the time for you to make snapshots over days so that if there's any features, you may be able to measure them as it rotates directly. Okay? So that is the interesting part. However, the problem is that it's in the northern hemisphere. So here's the basic physics of it. You saw these jets, which are very beautiful in the picture that Jim showed you for SNA, but this one in M87 in Virgo, it already can be seen even in the optical. Okay, so this is an optical picture where you can see the jet already coming out, emerging from the center. But the interesting, of course, is that in the radio, we are constantly improving the angular resolution by sharpening the array size, sharpening the wavelength, and as you keep going down in magnification, it keeps on getting better and better, always showing a jet. Okay? So this is the second property of M87 that's very important as compared to the galactic center, which is that already we know there is a jet coming from the center of the system. Okay, so the question is, does it look like what the artist thinks? So, what are the basic properties of this? Okay, how do we know that there is a black hole there? So actually it goes back to the spectroscopy. Okay. So this is very similar to the experiment that Jim has done, of course, in the famous case where he sees the masers rotating in a disk around the center of the galaxy. In this case, in NDC 4258, in this case, the optical spectroscopy also can track the motion as you go across. Okay, so they see this nice Keplerian path, and that which you can fit, and using the distance, you can calculate this mass. This is how we deduce that the mass has to be quite high in this particular system. So that's the optical measurement. And that's the radio measurement, which I told you about. With the VLBA, you can actually image the jet all the way down. Okay? And this particular imaging is quite interesting, which I'll come back to. But based upon this calculation, that we expect the shadow will be on the order of 20 to 40 micro arc seconds. So here it is. This is what it ought to look like if we had, depending on the black hole, right? So optically thin flow, optically thick flow, geometrically thin disk, spherical flow. Its image will appear different depending on how it looks. Okay? So here's the interesting question, which is that in this particular case, we can actually measure the width of the jet as a function of distance to the central source. And this series of VLBI experiments basically shows that the width of the jet continuously decreases in a pattern that follows a parabolic streamline. Okay? In other words, that jet has a parabolic shape as it goes down. Because of this parabolic shape, you can deduce how far to project down to the throat of the center. And here they project into an interesting region. Okay? This is just a normal rotating black hole, supermassive black hole, and this one is actually a rotating one. Okay? So by even the projection of the jet, you'll be able to get information of supermassive black hole. And here's a more sophisticated model where you actually calculate the jet and calculate the black hole shadow. And here was calculation by Broderick and Lowe, adding the armor, sharpen the image from the blue dot to the yellow dot. Okay? So this is what you need in M87 in order to resolve the structures. Of course, what we're going to do is to add the Greenland telescope, which will sharpen the resolution by a factor of 2. So what does it look like? There's the baseline that Jim showed you. There's the best case that we can do in the galactic center. Okay? The interesting thing, of course, is that even on the baseline that we're measuring, we already see the fringes going down. Okay? So at this point, of course, most people say, oh, but you're already running out of signal. Why do you want to build an even longer baseline, right? And that's the question, meaning that this is not very satisfying because it is only fringing with a pair baseline. Okay? What you want is an image. And that's why you want to build an array, right? So Jim shows you that. You know, this is what it looks like. You know how to build the event horizon telescope. And here's a list of telescopes that we could use. Here are the ones that are functioning, including the Mexican LMT, which will be coming online. ALMA is coming online. And then there's various other telescopes that we can use, right? But what we want to do for M87 is to establish this particular triangle. As you can see, it also adds many baselines on top of the current one, which is this one. Okay? And then with the LMT, with ALMA. And the longest baseline, that is to leverage the existence of SMA and ALMA. ALMA is very important because the sensitivity goes as the geometric mean of the area, the collecting area. So increasing the collecting area tremendously by ALMA gives us that sensitivity. Okay? And the site has very good transmission, very low water vapor. How do we know that? Of course, we are testing. Okay? So to build the first Arctic observatory, in a sense, you need all of these things, right? You need low water vapor, which you can achieve by high mountaintop deserts, and then also stable atmospheric conditions in order to maintain that fringe stability. And then, of course, you want a very long baseline, mutual visibility with these. From that, there are only so many places you can do. And here we are. That's the triangle, right? From Summit Camp on top of Greenland, and then ALMA, and then SMA. And here's the UV tracks, which shows you that the red ones are filling in the long spacing by roughly a factor of 2. Okay? And then here's the sky condition, measuring the sky condition. Here's the color diagram. Okay? Blue is good, and you can see that in the middle here, there's not much good, right? Except for Chile. Okay? Pole is very good, and the Arctic, when it reaches down to Greenland, it is also good. Okay? So, you know, there's good spots possibly in China, but the problem is that there's no visibility. Okay? No mutual visibility. So the question is, how cold is it? We send our staff there, and we stand there to see whether they freeze or not. They came back, so I guess it's cold enough, but workable. And then we also set up equipment. This is one of the test equipment which we put out there in 2011, immediately following the telescope being awarded to us. We checked the atmosphere by sending out this tipping radiometer, which we tested in Hawaii, then we tested in Pearl Station, which is next to this is the Eureka Station, next to Greenland. And the site is not good enough, and then we moved it to the Greenland itself to measure. And during this time that we've been measuring the transparency is less than 0.06 for 50% of the time. Best observatory in the Northern Hemisphere. Okay? And you can see that by comparing the mean water vapor content, mean precipitable water vapor. You can see that Mauna Kea is out here, and the Summit Station is just much better. Okay? With such an atmosphere, of course, then the transmission is almost comparable to the high spot called Sinica. I can never pronounce this word. It is the site which is 500 meters higher than the ALMA site. Okay? 500 meters will get you above the inversion layer, and then you begin to have open windows, even in these bands beyond the paracles. Okay, I have no time to discuss this about the single dish work, but the single dish work is also very important because you're opening that window. And this argument, the advantage of terahertz, is the same argument we used for submillimeter array when we built it, namely that the dust is scaling as nu to the 4, spectral line is scaling as nu to the fifth, which allow you to attack things that are much fainter that you cannot see before. Here we are. This is the prototype telescope, which was located in New Mexico. This is the production antenna. It's essentially the same, except of course the structure, superstructures are a little bit different. But the key here is that can it survive polar conditions? Here's a little description of the antenna. Okay? The most important part is the weight. It is a heavy piece of equipment. Okay? So that is the principal problem of this telescope, which I'll explain. But in 2011, we sent an engineering team out to examine the telescope to see whether it was still okay. And we examined the parts, and they're all okay. But that's not good enough, because okay just means that it's okay in New Mexico. Is it okay at the pole, right? So the engineering study says, no, it is not. And therefore, this past year, we had another engineering team going out there, completely disassembling the thing. And we are going to be shipping, various parts already shipped, and most of it will be shipped out to various engineers, to do the retrofitting, to get the operation down to minus 60 C. Okay? Minus 60 is pretty cold. So the steel itself becomes a problem, not only the lubricant. So various parts needs to be made. At the same time, we are worrying about the receiver systems. We are adopting the ARMA system as much as possible. This is a receiver cryostat that was actually used for the ARMA Japan part. This is the receiver cryostat for testing their telescope. We are making use of standard ARMA production inserts. The reason for that is to standardize the equipment for VLBA experiment with ARMA. You want the equipment to be as similar as possible. And then we're developing the recorder together with Haystack, and this is our junction fabrication facilities in Taiwan. And at higher frequency, we're working on the terahertz, and this is in Taiwan. We're producing this kind of HEV, hot electron bolometer mixers, and with the potential of building focal plane arrays. This is an effort that we're doing in Taiwan. There's a parallel effort also at Smithsonian. Okay, so the main problem, as I said, is the weight. Okay, the weight of the telescope is quite high, and the size is also quite large. Okay, they're exceeding 6 meters for the main pieces, and this makes it that it's impossible to fly it in. Okay, basically, the plane that can land there, a C-130, simply is not large enough to fit these pieces in. Okay, so land traverse becomes the principal item. So you have to go through and you break down all the pieces and check all the weight, check all the sizes, and then we check it against so-called land traverse, which means to drag the thing across the ice sheet. Okay? Drag the thing across the ice sheet has been done before. This is how they bring fuel to the site and bring containers to the site. So in the past, we have been studying this with the engineering firms to calculate the cost, time, how to do it. In addition, we need to build a snow foundation because it's not rock, so you need to pack the snow. Why? Because the snow density needs to be increased. Okay? Only by packing the snow, by running a bulldozer over it with 6-inch lifts, you have to layer by layer running the snow over and over again and pack the snow down until it is solid, as solid as can be, to a depth of about 30 feet, almost the size of a football field, we estimate. So this will be principally an engineering problem. Okay? And then on top of that is a steel frame. We need 3 times bigger foundation than the South Pole because every year the snow actually is quite a lot more snow up there than in the South Pole. So here's what it looks like. You build a wooden platform on top of this compacted snow, and on top of that you have a steel frame like so, to preserve the stiffness of the platform that you will use on top to build the telescope, for the telescope. And then the telescope sit on top. This is the model from the South Pole. We're following it. This is an engineering solution of how to put the telescope on top of this snow foundation. So this is what it will look like, similar to this. Our current study shows that we'll probably disconnect the office from the telescope because in fact this particular path is a problem because it is a heat conduction process which leads to shifting of the structure here. So we will isolate these two. How to get there? This is our logistic plan. On the left here you can see the VLA. The 3 telescopes are the 3 little dots over here that you cannot see. These are the actual VLA antennas, but the 3 of them are down here somewhere. One already has been retrofitted. The Japanese one is retrofitted, and it's already part armor. And we've just taken apart the second one, and it's in pieces to be shipped. After retrofit, it will come to Norfolk Naval Station. Here's the proposed spot where we'll stage our stuff and then put on the slip here where this boat will be taking us. Here you can see an aircraft carrier. This boat goes only to Thule once a year. It gets to this deep water port. It is only open 1 month a year. So very important, we have to get on the boat, to make the boat to get there. Once we get there, there's an Air Force base from which we will do our staging, we will do the assembly and do the first test and first observations from that Air Force base. After that, we'll disassemble and then drag it across the snow. For smaller pieces, we can fly it in on C-130. During the winter months, we can still get in on a small plane. Maybe Jim would like to fly it. Would that be exciting, Barbara? And then we have to build up the facilities. So here it is, Greenland. And here's just a little short movie to show that, it's cold, but it's workable in the summer months. You can drive along fairly easily. I mean, these are maintained by the Air Force. It's in good conditions. There are sleeping quarters, offices, and then there are warehouses that we will make use of when we get there. We already have been on site with the Air Force to discuss with them what our plans are. Of course, before we bring any equipment, they always say, no problem, fine, come. When we show up at the boat, then we'll see whether it's fine or not, right? But the hope is that it will be fine to get there and to use it. And here, on the right-hand side, is just showing you one of these traverse, here's the containers. You have to drag along containers to sleep on because the traverse will take 3 or 4 weeks. And then here it is, dragging equipment and so on. So this is the number one equipment that we need to buy. Here you can see that there are 2 tractors pulling, and that's because there's actually a little bit of an upslope in order to get to the ice sheet from the beginning part. So that upslope part, actually, we need to do a double pull in order to get that weight across the ice sheet. Okay, so here are the things that we need to do, and things that, sort of a laundry list of things that we've been doing. So basically, in these 2 years, we've been working hard, testing the site on the summit, retrofitting the telescope, allocating budget, identifying Air Force base, naval base, formal proposal to NSF. No budget is being requested, but we need to negotiate an agreement with them for them to support us logistically, and then potentially downstream to share infrastructure. And NSF is acquiring, it's under their command to, under their task to acquire the site. Actually, this site is no longer called Apex. There's another name. What's the name, Jim? It's EPEC or something. Some Greenland word for the eye. Okay? So that's ongoing. And then we're disassembling the telescope. We've already secured the hydrogen maser standard. We procured a prototype cryostat. We are in the process of acquiring the inserts from Band 7 from Iran. And then internally, we have used our budget to start the retrofit process. We have a request to Academy for the budget at the end of last year, of which we got $1 million. We have another path looking for more budget that's ongoing under negotiation. And as to LMT itself, we're looking to build a receiver system for David. And this is also part of the interesting thing to set up for the BLBI effort in the middle of that triangle where the baselines would be. Okay? And then we're also working on a correlator. So here's the summary. First major Arctic observatory. What we have up there right now is studying ice, studying the atmosphere, but not an observatory. Of course, in the Antarctic, there's quite a facility down there, but Northern Hemisphere also have half of the sky, right? So it deserves to be studied. And the goal is to achieve the highest angular resolution in astronomy, direct proof that we have the black hole by imaging it, measure the mass and spin for the first time, wide field imaging for the first time in terahertz, and then of course this team that I've mentioned and the assets that we have, namely that we already have the SMA between SAO and IA, and we're invested in ALMA, and now we'll build the Greenland telescope. It's very important because in submillimeter wavelengths, these 3 will be the only 3 sites that will support the observations beyond about 300 gigahertz. The other site is not going to be good enough, okay? So, why do we do this? Because it's hard. And here we are. We are waiting for a team to lead us. You might say, why is there a dog sled in this project? Well, it turns out one of the major difficulties in Greenland, as in any glacial environment, is that there will be fissures that will be developing during the winter as it melts and frost and melt and frost. Okay? So there will be these crevasses that will appear that you could drive over and drop your $10 million worth of equipment in. So we very much want to not do that. So first we will have satellite imaging of the ground, to locate the crevasses. And then in front of the main team, there's also a smaller tractor with a forward scanning radar to look under the ice to see whether there are any hidden crevasses. But of course I'm still worried about that, right? Because even those tractors are kind of expensive. So I thought maybe we could have some graduate students head of that team or something. Okay, 2016, this is what we're looking for. The telescope on the site looking at the jets. Oh, stop there.
Paul, you seem to have left out one item in your long list of things that needs to be done, and that is, you project the operation and maintenance cost of the annual cost?
The operation cost we project is $4 million a year.
That includes maintenance as well, doesn't it?
Well, maintenance, but I think the main problem is fuel. Okay? You have to remember, every gallon of diesel has to be flown out or dragged out. And the project, we project that we'll need about 100 kilowatt. Now, you might say, that's a lot of fuel, right? 100 kilowatt. But in the South Pole, they have a megawatt station. Okay? 150 flights a year just to bring fuel. So I'm thinking how to get around that. Okay? So I have some ideas, so it doesn't work because it's dark. What else? Wind energy. Okay? Wind actually has a steady wind, a few meters per second at the pole. The problem is it's cold. Okay? Any mechanical structure built in that environment may freeze up. So this is a fundamental engineering problem. So I'm looking to find a donor in a company which would be interested in this particular problem of energy generation by wind in a very cold environment. Of course, a wind farm in a cold environment would be very good because nobody wants to live there. Nobody will complain that you have wind farm there, so you just generate the electricity. So from our team point of view, we're going to generate that electricity and then we'll go to the NSF and say, hey, want to buy some electricity? That's how we solve the operation.
Good luck.
Don't say good luck. Come and work on it. Show some stuff.
Once this telescope is ready, how long will it take to image the black hole, to see the shadow?
Well, I think the project will take 5 or 10 years. The initial experiment, of course, will be at the low frequencies to establish the fringing and the stability of the instrument. And then, of course, we immediately get onto that as fast as possible. What you don't see, I didn't go back and show you the atmospheric transmission from, of course, right now we cannot really compare the atmosphere except from these radio sound measurements. Okay? But the data shows that in a couple of months, probably February, March, January are our best months, when actually the conditions are as good as the South Pole and when ALMA is also very good. So those would be the months every year that would be on this problem to try to beat it down, right? So how much time? I would like to think 5 years. Why is that? Because I'm kind of old, I'd like to see it done.
I will have to write that one down. I heard him say it. He said he was old.
Confess to that. You guys are old, so it's okay.
Other questions? Okay, Ron. Please.
Yes, how many sources do you have? Because the galactic center you cannot see with this configuration, but how many sources apart from one?
No, there are a couple more things. One's a little risky, right? But you have to think of this, okay? It's not an observatory. Okay? Good science is a physics experiment. You know, I remember when I was an undergrad studying physics, you know, one of the things I worried a lot about, because I was trained as a laboratory physicist. You know, you build equipment, it takes you 3 years, 4 years, you take one data point, take it apart, build a new instrument again. I was so frustrated by that at the end of my 4 years, you know, I thought, maybe I should do something better that has data, like a telescope. But you know, after these years, you know, I'm going back to building instruments again, you know, which is...
Could you say a little bit about the terahertz single dish experiments? In particular related, how does it compare to APEX or SOFIA?
Yes. On any flying instruments, of course, on satellite is best because you want to get above the atmosphere. But SOFIA is very good. You know, it gets above most of the atmosphere. It's above us, so you will have very good transparency, right? The difference, of course, is that SOFIA is a small aperture. This one has a much bigger collecting area. So it's similar to APEX in the sense that, you know, it's the same aperture, roughly the same altitude, but it's a little better sometime a year. So it is really about being able to operate with the right equipment. Okay? So it's similar in some sense to CCAT, which is at the same size. Okay? But CCAT is somewhat later because it actually has to raise quite a bit of money, you know, go ahead. And there is a gap between they are ready and our intention is to be there before them, trying to do the science. And we are talking with these people who are building instruments for CCAT so that they can come and do the equipment in our facility. Okay? So that's the goal. The science, what is the science? Actually, when we built the submillimeter array, we really didn't want to work in the submillimeter. Actually, we would prefer to work in the far infrared. Reason? The radiation curve for most of the universe peaks in the far infrared, right? So the higher frequency you go, that nu to the fourth, nu to the fifth really helps. And that's what we're after.
So it's both the best part and
the line. And the line, right? It goes as nu to the fifth because the Einstein A scales as nu to the 3, which means that all the faint radiative processes, which we could not detect, either because of the low column, right, or the faint signature, now you multiply it by nu to the fifth, and there you are. We've shown and proved that in the submillimeter regime, right? As you know, in centimeter wave, you know, you go gigahertz, click, one line, right? Submillimeter, a forest of lines, right? That's the nu to the fifth. That's it.
Yeah. Are you sensitive to the black hole in Andromeda?
Am I sensitive to the...
To the black hole in Andromeda, which is a 10 to the 8 solar mass?
10 to the 8, so, you know, it is a, yeah, I mean, you know, it depends on how bright it is, right? It scales linearly, so the project size will be big, right, because it is bigger than the galactic center. So it might be possible, but I don't know how bright, you know how bright it is?
very faint. Very.
Oh, Jim gives the thumbs down. Oh, now he's being polite.